Hello everyone, my name is Jinan Reddy and I'm a CSC data science student at Iare Hyderabad. In this video, I'm going to explain about the graph and the graph isomorphism problem. The graph isomorphism problem. The graph isomorphism problem is a computational problem of determining whether two finite graphs are isomorphic. The problem is not known to be solvable in polynomial time, nor to be NP-complete, and therefore may be in the computational complexity class NP intermediate. It is known that the graph isomorphism problem is in the low hierarchy of class NP, which implies that it is not NP-complete unless the polynomial time hierarchy collapses to its second level. At the same time, isomorphism for many special classes of graphs can be solved in polynomial time, and in practice, graph isomorphism can often be solved efficiently. This problem is a special case of the subgraph isomorphism problem, which asks whether a given graph G contains a subgraph that is isomorphic to another given graph H. This problem is known as to be NP-complete. It is also known to be a special case of the non-abelian hidden subgroup problem over the symmetric group. In the area of image recognition, it is known as the exact graph matching. State of art. In November 2015, Laszlo Babai announced a quasi-polynomial time algorithm for all graphs that is one with running time. Display style 2 power O log n c of c, log n power c. For some fixed display style is c greater than 0. On January 4, 2017, Babai retracted the quasi-polynomial claim and stated a sub-exponential time bound instead of Harald Helfgott discovered a flaw in the proof. On January 9, 2017, Babai announced a correction published in full on January 19th and restored the quasi-polynomial chain with Helfgott confirming the fix. Helfgott further claims that one can take c equals to 3, so the running time is 2 power 0 of log n power 3. Prior to this, the best currently accepted theoretical algorithm was due to Baba and Lux 1993 and is based on the earlier work by Lux 1992 combined with the subfactorial algorithm of V and Zemlyachenko, Korinko, and Chidwick 1985. The algorithm has runtime of 2 power O root n log n for graphs with n vertices and relies on the classification of finite signal groups. Without the classification theorem, a slightly weaker bound 2 power O root n log n 2 n was obtained first for strongly regular graphs by Laszlo Babai 1990 and then extended to the general graphs by Babai and Lux 1993. Improvement of this exponent root over root n is a major open problem for the strongly regular graphs. This was done by Spielman 1996 for hypergraphs of bounded rank. A sub-exponential upper bound matching the case of graphs was obtained by Baba and Codinot 2008. Solve special cases. A number of important special cases of the graph isomorphism problem has efficient polynomial time solutions. First is three trees, planar graphs. In fact, planar graph isomorphism is in log space, a class contained in P. Interval graphs, permutation graphs, circlet graphs, bounded parameter graphs, that is, graphs of bounded tree with graphs of bounded genus. Planar graphs are graphs of genus O. Graphs of bounded degree, graphs with bounded eigenvalue multiplicity. A contrastable graphs, a generalization of bounded degree and bounded genus. Color preserving isomorphism of color graphs with bounded color multiplicity, that is, at most k vertices have the same color for x fixed k, is in class NC, which is a subclass of P. Complexity class GI. Since the graph isomorphism problem is neither known to be NP complete nor known to be traceable, tractable, researchers have sought to gain insight into the problem by defining a new class GI. The set of problems with a polynomial time during reduction to the graph isomorphism problem. If in fact the graph isomorphism problem is solvable in polynomial time, GI would equal P. On the other hand, if the problem is NP complete, GI would equal NP and all problems with NP would be solvable in quasi-polynomial time. As is common for complexity classes within the polynomial time hierarchy, a problem is called GI hard if there is a polynomial time during reduction from any problem in GI to that problem. That is, a polynomial time solution to a GI hard problem would yield an polynomial time solution to the graph isomorphism problem and so problems in GI. A problem display style X is called complete for GI or GI complete. If it is both, GI had a polynomial time solution to the GI problem would yield a polynomial time solution display style X. The graph isomorphism problem is contained in both NP and COM. GI is contained in and low parity P as well as contained in the potentially much smaller class SPP. That it lies in parity P means that the graph isomorphism problem is no more harder than determining whether a polynomial time non-deterministic Turing machine has an ever or odd number of accepting paths. GI is also contained in a and low fuzzy BP and P. This essentially means that the efficient Las Vegas algorithm with access to an NP oracle can solve graph isomorphism so easily that that it gains no power from being given to ability to do in constant time. GI complete and GI hard problems. Isomorphism of other objects. There are a number of classes of mathematical objects for which the problem of isomorphism is a GI complete problem. A number of them are graphs endowed and with additional properties or restrictions. Digraphs, label graphs with the problem so that is isomorphism is not required to preserve the labels, but only the equivalence relation consisting of pairs or vertices with the same label. Polarized graphs, made of a complete graph game and an empty graph game, plus some edges connecting the two. Their isomorphism must preserve the partition. Two-colored graphs, explicitly given finite structures, multigraphs, hypergraphs, finite automata, Markov decision processes, commutative class 3, nilpotent, that is xyz equals to 0 for every element xyz semigroups. Finite rank associated algebra over a fixed algebraically closed field with 0 square radical and commutative factor over the radical. Context-free grammars, balanced incomplete block designs, recognizing combinatorial isomorphism of convex polytypes represented by vertex facet indices. GI complete classes of graphs. A class of graphs is called GI complete if recognition of isomorphism for graphs from the subclass is a GI complete problem. The following classes are GI complete: connected graphs, graphs of diameter 2 and radius 1, directed acyclic graphs, regular graphs, bipartite graphs without non-trivial, strongly regular subgraphs, bipartite Eurarian graphs, bipartite regular graphs, line graphs, split graphs, caudal graphs, regular self-complementary graphs, polytopic graphs of general simple and simplicical convex polytypes in arbitrary dimensions. Many classes of graphs are also GI complete. Other GI complete problems. There are also non-trivial GI complete problems in addition to isomorphism problems. The recognition of self-complementarity of a graph or diagram. A click problem for a class of so-called M graphs. It is shown that finding an isomorphism for n vertex graph is equivalent to finding an n click in an M graph of size n square. This fact is interesting because the problem of finding an n minus sigma click in a M graph of size n square is an NP complete for arbitrarily small positive sigma. The problem of homeomorphism of two complexes. J hard problems. The problem of counting the number of isomorphisms between the two graphs is polynomially time equivalent to the problem of telling whether even one exists. The problem of deciding whether two convex polytypes, polytopes given by either the V description or H description are positively or affinely isomorphic. The latter means existence of a projective or affine map between the spaces that contain the two polytypes, not necessarily of the same dimension, with induced bijection between the polytopes. Program check. Manuel Blum and Sampath Khanna, 1995, has shown a probabilistic checker for programs on graph isomorphism. Suppose P is a claimed polynomial time procedure that checks if two graphs are isomorphic, but it is not trusted. To check if graphs G and H are isomorphic, ask P whether G and H are isomorphic. If the answer is yes, attempt to construct an isomorphism using P as a protein. Mark a vertex U in G and V in H and modify the graphs to make them distinctive with small local change. Ask P if the modified graphs are isomorphic. If no, change V to the different vertex. Continue searching. Either the isomorphism will be found or P will contradict itself. If the answer is no, perform the following 100 times. Choose randomly G and H and randomly permute its vertices. Ask P if the graph is isomorphic to G and H, as in M protocol for graph 9 on isomorphism. If any of the tests are failed, judge P as invalid program. Otherwise, answer no. This procedure is a polynomial time and gives the correct answer if P is a correct program for graph isomorphism. If P is not a correct program but answers correctly on GNH, the checker will either give the correct answer or detect invalid behavior of P. If P is not a correct program and answers incorrectly on GNH, the checker will detect invalid behavior of P with high probability or answer wrong with probability 2 power minus 100. Notably, P is only used as a black box applications. Graphs are commonly used to encode structural information in many fields, including computer vision and pattern recognition, and graph matching, that is, identification of similarities between graphs, as an important tools in these areas. In these areas, graph isomorphism problem is known as the exact graph matching. The chemoformatics and in mathematical chemistry, graph isomorphism testing is used to identify chemical compound within a chemical database. Also, in organic mathematical chemistry graph, isomorphism testing is useful for generation of molecular graphs and for computer synthesis. Chemical database searching is an example of graphical data mining, where the data canonization approach is often used. In particular, number of identifiers for chemical substances such as miles and inch yield designed to provide a standard and human-readable way to encode molecular information and to facilitate the search for such information in databases and on web. Use canonization step in their computation, which is essentially the canonization of the graph which represents the molecule. In electronic design automation graph, isomorphism is the basis of layout versus schematic circuit design step, which is a verification whether the electric circuits represented by the circuit schematic and an integrated circuit layout are the same. So, thank you.